Hi guys, nice to, well, I'd say nice to see you, except of course I can't see you. Right, I'm gonna do a few more videos on NMR, Proton NMR spectroscopy, which I hope, well, basically I'm intending to get right to the end of NMR spectroscopy, which will take me probably, it's quite complicated, so you know, it'll take me probably a few more videos to get done. It's not something you can just do like that. This video is going to be about splitting of the low resolution peaks by protons on adjacent carbons. So, and this is like the last part of the NMR and the toughest part of the NMR, really. And then you can use this to deduce the structure of different molecules, which I intend to have a bit of a look at with you. It's pouring me rain, so there's nothing else to be done. Nothing else going on, really. Yeah. I hope you're all well, of course. If you're really bored, have a look at this. I'm going to send an email with some packs for you to have a look at and maybe have a go at if you feel like it. Yeah, and you know, at least you can say if you do the stuff, well, okay, I completed the course, I completed the A-level course, okay, which I think is important. Yeah, so it'll take me a few more videos to sort that out, but without further ado, let's go to the last, most trickiest part of the whole thing, which is, like I say, splitting of peaks, spin-spin coupling, as it's actually called. Right, okay, let's go. Okay, so spin, coupling, or is this known as splitting? There you go. Right. It's all based on something called the N+1 rule, which you won't understand at all, totally unintelligible until we apply it. Okay? So, the N+1 rule is this. If we have N being a number, protons, on an adjacent, underline that word, on an adjacent carbon, the number of peaks the peaks I prefer, or the peak from the protons on the carbon in question will be split N+1 times. Now that sounds completely and utterly unintelligible, I understand that, but it's not too bad. I think the whole thing about this is you look at the carbon, you look at the protons on a particular carbon, and then you look on the carbons next to it, adjacent, and if they have protons on them, they will interfere and split the low resolution peak of the protons of the carbon that you are looking at. If there's, say, 2 protons on an adjacent carbon, it will split the peak of the protons of the carbon you're looking at 3 times. If there are 3 protons, such as a methyl group, on a carbon, if there is a carbon joined to that, the peak that gives the peak that is generated from those protons will be split 4 times. You will see what I mean. But what you have to do, you have to be a bit counterintuitive, and you have to look backwards. That's where it's tricky. You've got to use your brain for this. There's no other way to do it, and you've got to practice it. Okay, but that's the theory behind it. Now we get rid of that. Okay, and I'm going to get rid of that because I need the space. We'll do our first, and I'm going to just blast these and see how you go. Okay. Right, so let's have a look at this particular thing, shall we? Esters, again, very important, quite common really. So I'm going to put this ester on the board. CH3, cool. O. Double bond. I've sort of done it backwards, I don't know why. Okay, CH2, CH3, an ester. I've done it backwards, but it doesn't matter. All right. Now, first of all, I'm going to do 2 spectra. 1, 2. Okay. This is whatever it is on this scale. Think I need to go up to about 6. This could all go wrong. 3, 0, 6. I'll go up to 6. 6, 3, 0. Low resolution, high resolution. This one, I'll show the very first splitting patterns that you've ever seen. Right, again, let's break this one down quickly. I'll go to red and let's have a look. You've got 3 different proton environments. Environment 1, environment 2, and environment 3. Okay, then as I always say, be strict with yourself and do a table. Okay, so over here, number 1, environment. Chemical shift, integration. We'll stick with that. First one, RCH, methyl group, stuck out on its own. Chemical shift 0.5 to 2. Integration 3. 3 in that environment. This one, number 2, refer to your data sheet. That is this H joined to a C, joined to another C, double bond O. Chemical shift on that, 2 to 3. How many in that environment? 2. H is joined to a C, joined to a C, double bond O. Last but not least, number 3. H, C, single bond O. Chemical shift 3 to 4, 3 in that environment. There you go. So, armed with that information, I reckon I can do what will essentially be 3 peaks. Okay, so we'll do this. Number 1, 3. So really I need to do 1, 2, 3, 4, 5, 6. So in this environment there's a peak there. Okay, 2 to 3. Yeah. 2 in that environment. 3 to 4. There you go. Right, I think that's okay. Let's do an integration for that, shall we? to red. Let me just check I've got it right. Those three there. Responsible for that. Integration of 3. Okay, definitely. There they are. Okay. These two here, 2 to 3 are those. So 1. So those two here, getting that peak, integration of 2. This one here, integration of 3. I think that's okay. Think so. Right, now let's go for it. High res. Looks different. When you actually see these in an exam, these peaks, as I've called them, I've deliberately drawn them fat to give this idea that they're going to be split, and they do get split, and they get split into very thin lines, okay, with specific sorts of names, okay. But straight away we go into this. You draw a line along the bottom. This is what an NMR spectrum really looks like, okay. Then we break it down, and I'm going from the left hand side first. Right, 3 protons on that carbon. Are they going to be split? Is there an adjacent carbon, adjacent next to it, adjacent carbon with protons on? Look adjacent? No, there most certainly isn't. Those 3 there are isolated. There is no adjacent carbon with protons on. They are not split. So in a real NMR spectrum, you would see, rather than a fatty sort of thing, a thin line, unsplit. Okay? And that line will correspond to those 3 there. The integration peak will be overlaid on top to tell you, you know, the relative areas and how many are in there, sure, but you get a thin line, not a fat thing like that. Okay, now let's go to the business end. Here, 2 protons on a carbon, okay. In that environment, everything's sorted. There it is, look. I should put a 2 there and a 1 there. Right, so those 2, are they going to be split? Is there an adjacent carbon? Yes, there's 2. There's an adjacent carbon there and there's an adjacent carbon there. Do those adjacent carbons have protons on them? That one doesn't, fortunately, so it can get a bit complicated. That one does. Right, so, and how many are on that adjacent carbon? So we're looking, the one we're looking at is this here, right? This peak here. We need to determine how much it's going to be split. Yes, there's an adjacent carbon with protons on it. So there are n. N is 3. There are 3 protons on the adjacent carbon to the one we're looking at. That is the thought process that's got to go on in your head. So the n+1 rule says that this peak here, produced by those 2 protons, is going to be split. N is 3, number on adjacent, n+1, 4. So this peak here, there, is going to be split into 4, and it's all based on Pascal's triangle for those sort of mathematicians amongst you. It's split into 4 and it looks like this, and you can't tell anything about the size of them. You have to look for the integration peak. So how high they are is irrelevant. 1, 2, 3, 4. That is how it is drawn. It should be the same position as the one. I'm a little bit to the right there, but in terms of chemical shift, it's centered around there. It's that peak split, okay. And n+1 rule, that tells me that the protons in that environment are attached to a carbon with 3 protons on it. You get used to this, believe me. So those of you who are on it, look at this one next. Sense here. Okay, 3 protons in that environment? Certainly. Attached to a carbon. Does the carbon have an adjacent carbon? Yes, it does. Does the adjacent carbon have protons on it? Yes, it does. How many are there? 2. Okay, so 2. N is 2. So those protons, the signal, the peak produced from those protons will be split n plus 1 3 times. And it looks like this when you're drawing a split of 3. It's all like it's like they're sort of drawn symmetrical, like that. That is your first proper NMR spectrum. Right, so in terms of doing a table for these in the exam, it's very similar to the one above it. So we'll have environment, delta, chemical shift, integration, with one more column, splitting. This is the table that you should produce whenever you get a spectrum and you have to analyse it, because of course you have to go the opposite direction ultimately, right? But imagine you've got this. Let's try and go in this direction. At any point you stop this video and you try and do it yourself. Complete this table yourself, okay, from this spectrum. Right, so I know what I need though to help you, because this won't tell you anything about how many, which is why the integration peak, which I suppose I'll put on over here, is so important. It's just the same as the one above. We haven't altered the number of protons in the environment. So 3, 2, 3. Okay, but you couldn't tell that from looking at these. Okay, and notice there's absolutely no correlation, obviously, between the integration peak and how much it's split into. There's 2 protons in that environment, but it's split into 4. There's 3 protons in that environment, but they're split into 3. So there's no relationship whatsoever between those numbers. They're generated in different ways. There's 3 protons in that environment, but there's no adjacent carbon with protons on it. So it's not been split. And you have to go backwards and deduce this. So I know this is easier than you might think, but let's try this. 3 to 4. So environment, you might want to put, well, first of all, you probably in the exam start with the chemical shift. Okay, now you've got to be precise. Now I'm on exam mode now. So that is, never mind the range, 3.5 chemical shift. You look at your data sheet, 3.5, that says HC single bond O. Yeah, integration tells me there are 3 in that environment, okay, and not split. The peak, there's a word, when there's not split, no adjacent carbon with protons on, not split. So it is called, not a single peak, it's called a singlet. Cool. An isolated peak, not split, is called a singlet. Number 2. I don't want that one there, it'll just confuse you. Can go in the opposite way, right? Okay, let's have a look at this one now, this one here. Right, so what's that telling me? It's telling me this probably is the, like I said, the first, when you go in the other way, this is the column that you start with, the chemical shift column. So between 2 and 3, but it's centered on about 2.4, midway, about 2, I don't know, 2.4, nearest whatever, okay, and then it's H. So 2.4, you look at your table in the exam, and it's HCC double bond O. Possibly. There are other things that can occur in that, okay, but you have to use a bit of this, okay? So it's telling me that there's that group there, which I would expect. I'm thinking now that this is an ester, because it's got all the ingredients for an ester, particularly those 3 being isolated in a singlet, okay? I'm sort of going backwards, and then flipped round, I'm sort of on this side of the molecule now, which is what I would expect to have this sort of situation with something on this side, something on that side with an ester. So that's on 2.4, and the integration is 2. Marks to be had for this. Okay, it's split into 4, which tells me there must be 3 next to it. Okay, split into 4, a special name, quartet. Isn't that lovely? Okay, and underneath, and this one, the last one, again, it's, let's say, centered on 0.7. Okay, and it is HCr, a methyl group, well away from the action. That's the way. Okay, integration wise, 3. I'm thinking a methyl group here, I'm thinking a methyl group, but I'm also thinking joined to a carbon with 2 protons on it. Why do I say that? Because this methyl group here, integration of 3, has been split in 2. Guess what we call that? Triplet. So there you are. Now, essentially, you should be able to take that spectrum, produce a table like I've done there, and then you've got to put your thinking cap on. Okay, looks to me like there's an ester, looks to me like the protons in that part of the ester, you draw it out, you play with it, you visualise it, are isolated because they've not been split, so there's nothing else going on there and they are isolated. Looks to me like the protons attached to that carbon, there's 2 of them, which is what I would expect. CH2 there, yeah, I'd expect that. That's backed up by that, in the right position for my ester, but split into 4. So that tells me that the protons there, those protons there, them because they're split into 4, they must be joined to another set, an adjacent set of protons, of which there are 3, to split these into 4. So I'm thinking a methyl attached to these 2. That would give me 4. Then I look at the N1. Okay, bearing that in mind, these 2 go together. Yeah, they go together, because then I'm looking at my H is on my methyl group right at the end, protons on the methyl group. Okay, yeah, they're right at the end, everything matches, and I'm saying if the one next to it, there's 2 protons, I'd expect this one to be split into 3, because there's 2 on that one, so they're sort of talking to each other. Yeah, they're sort of mutually sort of dependent on each other, these values, and they have been split into 3, triplet. So from that table I should be able to deduce that molecule with a bit of other information as well. But there's your splitting pattern right there. That's what it's all about. Right, I'm going to stop there, let that sink in, and I'm going to do some more in the next one. Okay, cheers guys, see you later.